So hi, I'm Cody. I'm a postdoc at MIT, working for LIGO Lab. Just to a couple things up front. One, even though I'm a LIGO person, I'm here presenting work I did with non-LIGO collaborators. And so my experience is a little different than a lot of people in the collaboration. And two, based on the talks I watched this morning, mine might be a little more physics heavy and a little less compute heavy. So I will do my best to answer any questions you have at the end about things that maybe you'll find more interesting or relevant. But with that exciting primer, let's jump right in. So I'm going to talk about a gravitational wave analysis that I've been running. But before talking about any sort of gravitational wave science, like it helps to make you all general relativists. So for those that don't know, general relativity, simply speaking, kind of you can think of it in two parts. One, it tells us that space and time are not, in fact, separate entities. They're part of a four-dimensional object that we creatively call space-time. And two, it turns out that space-time is warped, is deformed by mass and by energy. And it's actually these deformations, these changes to the geometry of space-time that we experience as gravity. So gravity is fundamentally very different from the other forces, and that it's this, in a way, it's a result of geometry that we can't see. So why is this relevant to gravitational waves? Well, general relativity predicts the existence of gravitational waves, which are very tiny ripples in the curvature of space-time. They travel at the speed of light, and they stretch and compress space. So what do I mean by that? So a classic example, if you've ever seen a LIGO talk before, buckle up, you're going to see a lot of the same images you've probably seen in the past. But what it means to stretch and compress space is, so I have a set of test particles over here, these dots, and if a gravitational wave were to come in directly to the screen, orthogonally, then what would happen is you would start to see the dots move something like this. And the interesting thing here, the thing that is, I think, blew my mind when I was an undergrad and saw this for the first time, is the dots aren't moving. This is actually space itself compressing. The distance between points is changing because of this gravitational wave rippling through. So these were first predicted in 1915 by Einstein. There's some very interesting history on the theory side of this, where there's a lot of arguing, and it wasn't until the 60s or 70s that theorists managed to convince themselves that this wasn't just some weird artifact of some numerical methods that they had to apply to solve these like really fancy differential equations. But finally in the 60s or 70s, they convinced themselves, yes, these are real. And then 100 years after they were first predicted, we detected them for the first time. They are, generally speaking, generated by basically non-spherically symmetric masses that are accelerating. So in the same way that in electromagnetism, if you remember your E&M classes, some of you are probably rolling your eyes like, yeah, right. But if a charge accelerates, it produces electromagnetic radiation. It's very similar in gravity with masses if they're not perfectly spherically symmetric. And you can think of the spherical symmetry. There's a nice analog with the beach ball where, ignoring friction, because I'm a physicist, and you put a beach ball in water and you let the beach ball, and perfectly spherical beach ball, right? Like, your favorite toy model thinking cap beach ball. As this thing rotates in the water, it's not going to make any ripples in the water. But then you add one element of reality to this beach ball, and it's got that little spigot that you can pull out to blow up and push back in. So it's got something that slightly breaks that perfect spherical symmetry. Now, whenever that goes in or out of the water, you're going to create a little ripple in the water. And that's the nice analog that helps me at least think about why is it non-spherically symmetric masses that make ripples in space-time. So, anything that's not perfectly spherically symmetric generates gravitational waves. But, obviously, you would think that if distance between points is changing a lot, we might notice that. So why don't we? Well, it's because you can think of space-time as an extremely rigid spring. It takes fantastic amounts of energy to do anything detectable. So the detections that we've made so far have been from the mergers of compact binaries. So, a binary star system, just two objects orbiting around a common center of mass. Compact binary just means they're compact objects, which is a way we quantify like how much mass something has and how wide it is, more or less. So compact basically means it's very, very, very dense and small. So for example, black holes and neutron stars are the compact objects that we usually look for. A neutron star maybe has a width of 10 kilometers or so, but it has the mass of like 9,000 pyramids of Giza. So per tablespoon. So a tablespoon has 9,000, pyramids of Giza in it. So extremely dense objects, very, very, very dense, very small. When these, so if you get these in a binary, because the system of the two of them is not perfectly spherically symmetric, they lose energy to gravitational waves. And it turns out that the rate at which they lose energy for these things is basically grows with the frequency of their orbital rotations. But when they lose energy, the way that works, what happens is the orbit shrinks a little bit, and then due to like the normal effects with conservation of momentum, et cetera, that you would expect, it speeds up. They start to orbit each other faster, and then they lose more energy, and then they orbit faster and they lose more energy, and it becomes this runaway process that it's 100 million plus years. But at the very, very end, you get these. So the first detection we ever made is two black holes, each about 30 times the mass of the sun, going right before they collide 2/3 the speed of light. And it's these sorts of fantastic amounts of energy in a collision that then moves our mirrors, our detectors, by less than the radius of a proton. So extremely stiff. We need extremely energetic explosions, effectively, of collisions in space to be able to detect these things. What's really nice about this, though, is the gravitational waves encode a lot of information about the objects themselves. So here is a typical gravitational waveform from just like some canonical compact binary, mass 1, mass 2 orbiting. You could see that what you're seeing here is a few things. One, the amplitude increases at some point until it reaches a maximum and then comes down, and the frequency massively increases here. So this is as you're at the very end of the waveform, right before they're about to collide, they're getting faster, 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 and they slam into each other. But the properties of the system that do this are encoded very heavily into the waveform. So you can see another example here where the second mass is the same size, but we've made the first mass much smaller. And you can see it has the same basic behavior, right? Like it's getting faster and faster and faster, and the amplitude is increasing until some point, and then they merge. But this is a much higher frequency. Whereas like if they were both bigger, for example, you would have maybe a much lower frequency waveform. And so they all share similar morphologies and similar behavior, but the waveform itself encodes tons of information about, so the masses, the spins, the location of where it's at, et cetera. So there's a lot of information that can be extracted from these gravitational waves about the sources that are generating them. So how do we detect them? So we have huge scale Michelson interferometers that there's a very simplified diagram here. So laser comes out of our conveniently labeled laser, goes into a beam splitter, and goes down two vacuum chambers. These here are lenses or mirrors. So the light goes in, bounces off, comes back in both of these and recombines. And again, if you remember your electromagnetism, when this happens, basically they will perfectly deconstruct with each other. So basically, if the light travels the same length down both of these, they're going to destructively interfere, and there's going to be no light coming out here. PD is photodiode, so where you see the recombination. But if they don't go exactly the same path or exactly the same length, then they won't exactly cancel each other out. And so we can use this information to say, okay, is the distance between these two arms different? And you can see here an example of what, a very exaggerated example, but an example of what a gravitational wave does to our detector as it passes through. So we have huge detectors. 2 in the US, 1 in Hanford, Washington. Washington's my home state, so I like to always show a picture of the Hanford detector. 1 in Livingston, Louisiana. There is a detector, or another detector, slightly different design, but same idea, in Italy called Virgo. And then Kagra is a detector that's currently up and coming in Japan. So in this picture, you can see these really long arms are what we shoot the lasers down. And here is where, the laser is housed and shot off into these arms. And these arms, their contacts are 4 kilometers long each. So these are very large scale experiments. And then finally, data analysis. What do I do? So I look for specific gravitational waveforms. We don't know which ones we look for, what are going to look for in advance, or are going to see in advance. So we look for like a million different ones. And we use match filtering, which the very basic idea is more or less you could do a sliding dot product of a waveform with some data that you've transformed, and you've applied some appropriate transformations to, and the output of the sliding dot product is directly proportional to the probability that there's a signal in the data. This is an oversimplification, but the punchline is here. So the blue up top is data, black is the waveform we're looking for, and the bottom red is SNR. You can see that there's a peak at about 1.5 seconds that is telling us that, okay, if there's a signal in here that looks like this black waveform, where it's at is at 1.5 seconds. So we do this a million times with a million different signals. Now, what I have been doing specifically, so everything I've talked about so far is just general compact binary gravitational wave science. What I've been doing with external collaborators outside of the LIGO collaboration is looking for systems that our normal analyses are not sensitive to. So black holes and neutron stars, it turns out, are really, really close to perfect spheres. Black holes are thought to be perfect spheres. Neutron stars are damn close to being perfectly spherically symmetric by themselves. We can parameterize the ability of, what if it's not a perfect sphere, with a parameter called kappa, which is, what specifically this is parameterizing is, realistically, if you spin something really, really fast, you're going to see some deformations. If there's like actual matter in there and it's not extremely rigid, you'll see deformations. So this, where, it'll squish down. So kappa parameterizes like how susceptible an object is to becoming oblate as it spins really, really fast. And it turns out, so kappa of 1 is like, it's not going to become oblate at all, no deformations at all. Black holes have a kappa of 1. Neutron stars have a kappa of like 5 to 10. We're still sorting it out, but it's small enough that we can still find neutron star signals without taking kappa into account in our waveforms. But once you get bigger than 10, the waveforms, again, the morphology, so to speak, doesn't change too much. They look very similar, but they dephase relative to these unity kappa waveforms that the LIGO collaboration is searching for. So you don't have to get kappa very large before LIGO analyses become completely insensitive to signals from these. So here's an example of the blue this is the exact same waveform. So okay, on the y-axis is the strain. This is just, think of this as the waveform. The x-axis is time. This is same masses, same distance, same spins, etc. The only difference between the blue and the orange is the kappa, which again is parameterizing like how oblate will it become as it spins up really, really fast. And you can see the waveform looks very, very similar, but they dephase from each other. So this is enough already at kappa equals 100 that if you were searching for the orange waveform with the blue waveform, you would not find it. So LIGO searches are completely insensitive, that have been done so far, are completely insensitive to these waveforms, to the point where, there could be, don't ask me to bet on it, but there could be, SNR 100 things hiding in the data that we don't see just because we're not looking with the right waveforms. So that's what my analysis has been working on with public data. Okay, so let's talk some analysis computery stuff. So a really high level view of the analysis workflow. So inputs, we've got, for my particular analysis, recall I said that there's 4 detectors, 2 LIGO detectors, 1 in Italy named Virgo, 1 in Japan named Kagra. For my particular analysis, I used public data, and we were trying to do this for as cheap as possible, so we just used the 2 LIGO detectors. So we had inputs from the LIGO site in Washington, the LIGO site in Louisiana, roughly 100 days of data at 16 kilohertz time series. And we looked for about 500,000 different gravitational waves, up to about 512 hertz. And these are, anywhere from 1 to 100 seconds long. We did the workflow in 5-day chunks. I'm going to show like an actual diagram here in a second, but basically measure the frequency spectrum of the noise, decompose the waveforms, because we do a lot of sliding dot products with lots of data. So it turns out that there's a lot of decompositions you could do to just reduce the number of floating point operations and all that good stuff. Filter the data, aggregate the statistics, and then assign significance and do data reduction, because there's just a large volume of data that we can't possibly save all of. We tried and we broke things. The data products that come out of this, the decomposed waveforms. So because we decompose them for floating point operations, we have to save them numerically. So it's about 50 gigabytes of information per 5 days of data. The reduced filter output, like after all our reductions, about 10 gigabytes. And that's, that it's reduced enough that it's not going to take up too much space, but also we can do studies on tweaking things about the significance estimate if our blinded results don't look right, without having to rerun everything. So that's really nice. And then the very final results only like 100 megs. So to Condor, we use DAGs. So everything we do is with Condor DAGs. And so what I have on the next page is a DAG workflow, and I'm going to have to switch my screen share for a second because we can't look too closely at this. But I did want to zoom in on one a little bit and show. So let me stop my share, screen share, pull up on an image that I can zoom into. So this is a DAG of the workflow. It's a few years out of date, to be honest, but the same general idea holds. This has been modified a bit to make integration with OSG easier. So, we have inputs from, this is basically the very first job where we are checking the frequency spectrum of the noise. All of that goes into some aggregation of frequency spectrum stuff. Here's where the decomposition happens in these, and these colors are broken up by the type of detector: Hanford, LIGO, Livingston, LIGO, Virgo. And then this is where you start getting into doing the actual filtering, but then starting some basic aggregation on, so you get into these two different workflows where, there's some filtering that's going to contain the actual results, but then in addition to the actual results, we want blinded results that we can look at before we unblind things, make sure we haven't made any mistakes. And we also want to inject, fake signals into the data and see, do we recover these? So we have an idea of is our analysis actually sensitive? And so you get into these two branching paths that reconverge down here at the bottom. I'm sorry, I have like a minute and a half left, so I'm starting to go really fast. Let me go back to the oh no, did I? Okay, there we go. All right, the clock is ticking. I will try to quickly go through this. So, okay, let me say something really quickly about OSG and IGWIN. So my experience with OSG has actually been using the public OSG pool. I have not used the IGWIN specific OSG pool, which is, it connects, all the general OSG resources to the LDG, LIGO data grid researches, but resources. But let me just say, the types of searches that I do lend themselves really, really naturally to high throughput computing workflows. But as I'm sure many of you know, many clusters are high performance and use, other schedulers. And we are so baked into Condor. And don't take that sounded like I was complaining. I'm really not, but Condor fits what we want to do very, very naturally. Our workflow just naturally produces DAGs, and OSG and IGWIN have been solved the wonderful problem for us of mapping our workflows on Condor to any cluster regardless of what they're running. So it's very useful for us. This is my collaborator list. Sorry I didn't say more about Condor usage, but I tried. I want you to know it's extremely useful to us. I will shut up now because I hit 20 minutes. I don't know if there's time for questions. Feel free to email me any technical questions you have that I didn't answer in my physics rambling. Thank you for listening.
All right, thank you, Cody.